don't know if I need to show it here as much. So, I've got it. Okay, got it. But these underwater flows, particularly when I give it to other audiences, is why I study turbidity currents. So I always like to show this slide that shows submarine fans on either side of India. And these systems built by turbidity currents are bigger than the Himalayan rivers. So turbidity currents are, by I think, almost any metric you use, one of the most important transport processes of mass of sediment around the surface of the planet. Traditionally, a lot of the work has been funded by oil and gas, looking for the deposits of turbidity currents, turbidites. Although I think there are more important reasons than that, particularly in the current stage of our planet, perhaps. So the underwater flows can also break cable systems. So over 99% of global data between continents, so Zoom calls, mobile phone traffic, transatlantic financial markets, they all travel through this cable network. And we got involved with the cable companies. It's this really interesting world. And these flows are one way of breaking not just one cable, but a whole series of cables, like the Grand Banks event, a famous event in 1929. In places such as offshore Taiwan, that's happened a number of times in recent years. It's happened offshore West Africa in 2020, which I'll talk about later on, during our project, in fact. And at least in West Africa, these cable breaks caused the bandwidth of the internet to slow from Nigeria to South Africa right in the middle of the first COVID lockdown when you needed the bandwidth. It took about 25 days to repair the cables. So these cables are actually pretty important, pretty strategic. If you saw the Tonga eruption, that eruption broke the only international cable to Tonga. So that really affected the relief efforts. So these cables, I think, are one of the most interesting reasons to study turbidity currents. Another one now is burial of organic carbon, mainly terrestrial, but also submarine organic carbon in the deep sea. That flux, as I'll cover later, can affect kind of atmospheric PCO2 climate over very long periods. But they could be a missing part of the carbon cycle. This image comes from over here in the Indus Fan. That line is a gas pipeline that's been proposed. As you can see, I would start to worry about where it gets to those sorts of locations, multi-billion-dollar projects. So a lot of the interest in these flows is not oil and gas anymore, I think. But on one level, they're just extremely large. And to try and convey the scale of these flows, I had a diagram. So it has the sediment mass within the individual flow in billions of tons, going up to values of the Grand Banks turbidity current there. And that was about 200 cubic kilometers of sediment. So to put that in context, all of the rivers in the world, so these are some other fluxes, all the rivers in the world provide about 7 cubic kilometers of sediment to the ocean each year, perhaps less than that nowadays with dams, maybe half of that. So the Grand Banks is way above it. And I'll talk about turbidity current in the Congo Canyon that eroded about 2 or 3 cubic kilometers of material. So maybe about a third to a half of all the sediment, all the rivers in the world every year. Over that side are some of the biggest volcanic eruptions going up to Tambora. So Tambora in 1815 does actually get beyond the Grand Banks, but things like Pinatubo, Tonga, Krakatoa are actually underneath it. So however you slice it and dice it, these underwater flows are volumetrically significant. Then I guess this is a fun slide to present here, actually, of all places. So this was a quote from a pretty seminal paper in the year 2000, Ben Meller and Claire Buckey, saying that geologically significant turbidity currents are impractical, brackets, impossible to study in action. So I guess there's already been work just over there, going back to Francis Shepherd, Dill, and all the people here, which was probably about as good as people had done to that point in 2000 to monitor flows in action, typically with single point current meters. Often with instruments that were damaged or lost. But outside of perhaps this group here, there's a view that it was impossible, impractical to measure these flows in action. We'll never do it. We'd have to go to the deposits, we'd have to go to balloon tanks and laboratories, numerically model it. And that persisted. So we started measuring the small flows. So these are time-lapse images from John Hughes Clark of bathymetry with Delta in Canada. And he also had M3 multi-beam sonars illuminating a turbidity current as a slide. So we showed it's possible in shallow water, the small flows. And then we got this as a paper review for one of the grad students. But you can't measure the really big flows, the ones that really matter. So in a second, I'll show you a flow from the Congo Canyon that went 1,000 kilometers. So some of it has just been shifting the view that this is not possible to do. And I'll come on to this kind of later on. This is from the Congo Canyon. These are turbidity currents. It's a time series in days. This is height above the seabed, the colours of the flow velocity from an IGPP. And that flow lasted for almost a week at a metre per second, not hours or minutes. So there are some surprises once you start measuring them. So the structure of what I'll go through, and if people have questions, just stop me as well. Please do. Is talk initially mainly about the Congo submarine fan of West Africa. So this is the most recent project, the biggest of the systems. And after that, I'll go back and try and do a run through the highlights, the scientific results, rather than methods from some of the other sites. So this is the Delta in Squamish in Canada, just north of Vancouver. That's about 1 kilometre. This is Monterey Canyon. So we did a project with Charlie Paul up at Mbari. That's about 50 kilometres. And then I'll start with the Congo system. That's about 1,000 kilometres. That's a bit more expensive than that. So I'll start with the Congo system and the most recent study that's only just published of this 1,000-kilometre flow. And then I'll try and go through some of the most basic questions about turbidity currents and try and, in 1 or 2 slides, just highlight what we found. And at the end, there's a little bit about where's the future of monitoring. And indeed, perhaps some of it could be around La Jolla Canyon, one of the most classic sites. So this is a paper that's published in Nature Commons about a year ago. Again, a big group of people. What we did is we put a series of moorings out along the Congo submarine canyon and channel. So this is West Africa. The mouth of the Congo River there is the second largest river for water discharge on Earth. The head of this canyon is actually inside the estuary of the river mouth. So that's one of the few systems that's really well completely connected. This is the upper canyon. So we dropped a series of moorings that as you guys will know, float at the top, anchor at the bottom, about 1 ton anchor here, acoustic releases. The ADCP is downward looking. So it looks at, it's about 85 meters above the seabed. You're getting data back on the velocities of particles in the flow with the resolution of a meter or several meters within the flow every 30 seconds. So we drop those off in slightly nervous fashion along the axis of the canyon, located them with the USBL to make sure they're actually on the axis, which mattered. We also, as I'll show later, put some ocean bottom seismometers out just outside the channel. So we put a cluster of them where we can get permits in Angola waters, and a cluster of them in international waters. These are some communication cables that later grow to give you some more information. This is the head of the Congo Canyon, 30 kilometers up into the river. So we'd monitor them in kind of intermediate and shallow water depths, and we were going for one of the big systems. We thought we'd get something, but we got rather more than we bargained for. So we put them in at the end of 2019 in September or October on a NERC research vessel. And then a couple of them broke during the December that followed, but then all of them broke between the 14th and 16th of January 2020. So I remember a train journey back from Southampton. They report back when they've surfaced and tell you their position. And the first one told me the position. I thought, this isn't good. And then later in the train journey, the second one came up. Well, that really isn't good. And by the time the third and fourth one come up, you know they're all going to come up. So we had this situation evolving through January, February, and then March 2020, just when the COVID pandemic was starting off, that all our kit was floating around a rather unfortunate part of the Gulf of Guinea, and that we really would like it back. They will report when they arrive at the sea surface, and you know the rise rate. So with some assumptions and hoping it pinged you when it arrived at the surface, you could get the time at which the mooring was broken on the seabed. So we had the sequence of flow speeds and transit times, but we quite wanted the ADCP data back. That gives us this 30-second resolution images into the preceding flows at least. So one of the backstories is that with help from the UK NERC group that run the research vessels, we actually managed to track them. This is my Google Earth image, and get back 9 of the 11 moorings. And I wouldn't bet on that. There are all sorts of things like we had to. So Durham wouldn't fund it. We had £300,000 of ship charters that we had to find £300,000 for. So people in Hull actually went to the finance department and director of NERC signed it off on Friday afternoon and we told about it on Thursday, but eventually we got it all back. The other thing that's floated apart from break our moorings is break both of the submarine cables across the two of the three submarine cables that went across the Congo Canyon. And this is what slowed the internet from Nigeria to Cape Town right during that first lockdown period. So the cable companies were trying to repair this, took them about 25 days. We actually chartered the cable repair vessel to go and get some of our moorings, and they were very good about that. So they definitely get a shout out. But I think in my career, the most surprising thing I'll ever see is we actually got some of these things back. So what did we find? This is a plot of the distance from the Congo River mouth, so that's the coastline or the estuary, going all the way out to 5 kilometres, almost 5 kilometres water depth, 1,200 kilometres. Positions are kind of these horizontal lines. So each of our ADCB moorings in the Upper Canyon are these dots here. And this goes through time, September, October, November, December, and January 2020. These are the cables in the middle, the SAT3 and the WAC cable. And these are our moorings in deep water. And the red lines are events that track through this array. And these are from the arrival times, you can get their flow speeds through the array. So there are quite a few events in the Upper Canyon. Many of them don't reach deep water. And then there's one event that's rather weak in deep water, but then the big one that just ripped up everything on the 14th to 16th of January. But one of the surprises we had is that in the canyon, the Upper Canyon, so this is at 2 kilometres water depth, and that's a single mooring ADCP time series, that's flow speed up to about 1.5, maybe 2 meters per second, some of the flows. And these are profiles above the seabed. It's active about 30% of the time. So the view that the Congo Canyon had big events or occasional events that were a few hours long and were very infrequent isn't true. It's active for about almost a third of the time. Individual flows in the Congo Canyon can last for over a week. So at least I would have predicted a few hours, not a few days or a week. So it's super active in the Upper Canyon. Then it kind of got more interesting. So the cables, they'd broken in January 2020. They broke again on the 9th of March 2020. And then they broke again actually in 2021. And just when we were trying to publish the paper with all the data, and they broke again in January 22. We had to update the paper at that point. Go for it.
Oh, I'm sorry. So can you explain what an ADCP record is?
Yeah, so the acoustic Doppler current profiler, is a system which emits a pulse of acoustic sound, which is reflected from particles in the flow. And the Doppler shift on the frequency that returns gives you the speed of the particles within the flow. And you do it at different distances or ranges from the instrument. So it's a way of measuring the velocity at a series of different points through a flow.
And the pulse is sent parallel to the flow or perpendicular to the flow?
Vertically looking down, so the flow is horizontal-ish along the seabed, and the mooring is housing an ADCP that looks vertically downwards. Okay. So it's a vertical profile through the flow.
So that only senses the flow directly below the mooring?
Yeah. It's got a footprint of a few tens of meters, but effectively it's a point below the mooring. And there are a series of these moorings, maybe 50 or 100 kilometers apart or more between the whole system. So they're point measurements, if you like.
Thanks.
The ADCP is rather bad at measuring the bottom few meters in the flow, but for technical reasons, it doesn't often return data there. They also have issues when they're being buffeted by the flow and they start flapping around. We don't get good data. And that tends to happen above a few meters per second. So they're often used in rivers, and I guess for many different oceanographic, often with kind of a 75 kilohertz, a bigger system. Yeah, keep stopping me if I go into jargon mode. Thank you. So that's kind of what we got. The first question you can go for is what triggered them? And bearing in mind those cables hadn't broken in that setting for the last, well, probably about 18 years. So going back to 2002, the cables had been there across the canyon but never broken. And then just before our first event in January 14th to 16th, the Congo River had a flood, which was its 50-year flood, the biggest since the 1960s. So we think the amount of sediment that flood brought into the Upper Canyon primed it. But importantly, the flow that we measured, the first one, happened after the flood peak. So it's not that the river water is full of sediment, it plunges, it forms what's called a hyperpictal flow. It waited for a week or two, and then it was triggered. And similarly, there was a 1 in 20-year flood here, but the other cable breaking flows are after that. So it waits for weeks or months before it goes, but it's probably primed by these big floods. And what we saw is that these events seem to coincide with low tides or spring tides. So this is the January event, this is the tidal cycle. March the 9th is on a spring tide, April 28th on spring tide. They're just been trying to get the paper to be published. This one decided not to be on spring tide, so it's 3 out of 4. But in general, in most cases, it seems that some combination of priming of the system by all the sediment from the flood, and then finally, weeks to months later, triggering at the spring tide, kicks off these events that go for 1,000 kilometers. So previously, like from the Grand Banks, we knew that earthquakes could trigger these big flows. But this is the first time that we could show how rivers are also triggering them, with some surprises that there is delays in spring tides, and able to connect the river floods effectively into the deep sea. So we never actually got into the mouth of the Congo River. We had a grant to do it, but we never managed to get there during COVID. But we have various ideas for why they're triggered at spring tides. One of which is to do with kind of release of gas bubbles within the sediment. We've seen that in other places. Another one is trapping of sediment during the kind of the ebb tides, and it's like an estuarine turbidity maximum. But it's kind of river floods and tides are what's driving it. The other thing is that the flood that triggered it is a 1 in 50 or 1 in 20-year flood. So previously, people thought the big earthquakes may trigger these sorts of scale of flows, but only every few hundred thousands of years. And these are happening every few decades, if that model's right. So they're more frequent, the big ones into the deep sea and these sorts of systems than perhaps we thought. So that was the triggering, and I'll come back to that point later on, but it's showing for the first time how kind of the big river systems connect into the deep sea pretty efficiently, actually. Every 50 or 20 years, you flush the canyon out. I'll come back to it later on, actually. Yeah, there's a point that the amount of sediment that was eroded by that flow was about 2.6 cubic kilometers of seabed sediment from time-lapse surveys. There's some uncertainties on that, but it's a huge amount. So I'll come back to that. This is a plot of the flow speeds with distance. So that's the coastline, and this is down to 1,200 kilometers offshore. Each one of these colored bars is an individual flow. So the one that really broke everything, the January one, is the black bar. So in the upper canyon, it's pretty good at maintaining just over 5 meters per second. These are average speeds of transit front velocities between the points. So they're averages, but about the same speed there. And it got a little bit quicker as it went further out into the deep sea, eventually reaching about 8 meters per second. So I put one of our German OBSs out as far as possible because I had to pay for it in case we didn't get it back. And I thought I'll put it as far out as I can. And unfortunately, this flow got bigger and bigger the further it went. So that was exactly the worst place to put it. We never got it back. But there's been this idea that these flows are just different to rivers. So these flows can pick up sediment from the seabed, get denser, therefore they go faster, therefore they erode the sediment from the seabed. So this just feeds back this loop until they ignite. And this is probably the first time of this scale of flow for sure, that there's really clear evidence they can accelerate. But as you can see, it's gone from 5 to 8 meters per second. It's taken over 1,000 kilometers to do that. So it is increasing in speed, but considering the distance involved, it's not a particularly rapid increase, spatially rapid increase. The other dotted lines are other events. So these are events in the upper canyon that never make it out into the rest of the array. These are some older data from the French, from Ifremer. And there seems to be a zone between about 4 and 5 meters per second at front speed, where if you get above that, it goes big, it starts to ignite. And if you're a little bit, just a little fraction underneath that threshold speed, it decays and dissipates and doesn't actually even get to the cables or the deep sea array. Some of them die here. So these, unlike a river, are kind of perched on a threshold. If they get above that speed, they can really become rather large. If they're just fractionally below it, they dissipate, they die out. So rivers don't really do that. They don't have those properties. So I'll come back to this plot again in a second. I'll show you that in other systems around the world, they also have a similar threshold. So Monterey Canyon has a plot like this, which is 50 kilometers long, 1,000. but looks very similar.
Is there a correlation with slope?
Good question. So the slope decreases from about 0.6 of a degree to 0.3 of a degree. From about here onwards, it's almost a linear profile. So it should be decelerating, if anything, on that, and it's going quicker. The width of it is the other one, and if you look at in the canyon, it's hard to know which width to choose. If we choose the first terrace height, that width is remarkably uniform through the whole system and through the channel. It's about 200 or 300 meters. And it gets slightly wider with distance, so it would act against that as well. So the container shape and the gradient must matter, but this manages to trump those and get bigger. So yeah, I think the other thing that was spectacular about the flow was the amount of erosion. So we had a survey, ship multi-beam survey from 2019, and then we're able to time lapse in 2020 after the flow. And there are various uncertainties in terms of trying to produce the time lapse differential elevation change on the seabeds, people may know. But the best estimate we have of that change cumulatively is about 2.6 cubic kilometers of missing material from the sea floor. So that material was flushed through the whole 1,000-kilometer system. Maybe it overbanked a bit, but most of it went out the end of the channel. It's a huge amount. It's equivalent to anywhere between 19 and 37% of the best guess of the river flux, annual river flux of sediment to the whole of the ocean from every river in the world. About a third of that went down just one submarine canyon over a couple of days in one part of the ocean. The other thing is the organic carbon. Mainly terrestrial organic carbon is relatively high within the Congo River and indeed within the offshore sediments. So TOC values are often 2.5 or 3%. So if you take an average TOC value and those volumes of sediment, you end up with about the same amount of terrestrial organic carbon flushed through this one event as all the rivers for a whole year. It's about comparable. So in terms of carbon budgets, this one submarine canyon was as efficient in moving carbon as everything else, all the other rivers in the world. So it's a pretty large volume. It's not as big as the Grand Banks, that was 200 cubic kilometers, but it's still pretty large. And this is the plot. So this is kind of a cartoon of the Congo Canyon plot that we had, that had velocity in meters per second and distance. So that was 1,000 kilometers to the Congo. We kind of did that. But we've now got this sort of data from a number of systems worldwide. And I thought it might be pretty random, but it's quite well behaved. So that's the Congo data we showed previously. In Monterey Canyon, you get above 4 or 5 meters per second. There were 3 flows in our 2-year deployment that went big. They were above the threshold. All the velocities underneath again. In Taiwan, there's some cable breaks. Again, you get above that 4 to 5 meters per second. You get big events. And even in the fjords in Canada that we worked in, the biggest events are only just making it to those speeds, but they go much further. And if you're a little bit slower, then you really don't go very far. So you can kind of collapse this into a plot which works for all the systems. So they're well behaved. There's something about this which is general, it's kind of universal. And it's probably once you erode enough sediment, you start to be able to sustain yourself. But what we're finding is the rate of an increase of flow speed was often very slow. And indeed, in some of the later events in Congo, the flow speed is pretty much uniform from the cable breaks. So there's a kind of model that these flows erode the seabed, get denser and faster, so get even bigger. So they should be doing that. Or they drop sediment out, get slower, drop even more sediment out, therefore get even slower and do that. But these are kind of different. They're like the igniting ones. They're picking up lots of sediment from the seabed, 2.5 cubic kilometers, I mean, a huge amount. Yet they're somehow sustaining a reasonably uniform speed. They're reaching near equilibrium. It might change a bit, but not much. So the kind of new model for that, this is the most basic kind of type of behavior of the flows, is that they'll erode the seabed and bring lots of material in into the front of the flow, but that material is often shed into the rear of the flow. The front of the flow is like running ahead as this thing that's driving the flow. There's a balance here between what's coming in and what the front is shedding into the rest of the flow. So the front stays about the same. So it's erosional, that's the old ignition model, but it's also in an equilibrium. So it's kind of understanding a little bit about how they work. And they're remarkably well behaved. I thought these plots would be much more inconsistent. But for once, we have data. So previously, we could hypothesize how these things work. For everybody had done it. There are lots of papers. So now we're actually got some data to test how they work.
What do you think is driving us? Like you mentioned, the slope is not a major issue, then gravity is now the driver.
I think it's the idea is you can exchange mass with the seabed. Unlike a river, the masses of sediment is driving the event. So you can have positive feedbacks, which depend on whether you're exchanging positively or negatively sediment with the seabed. So those sorts of processes seem to be dominating over changes in the gradient of the seabed, or indeed the width of the system, the channel or the canyon. Even though these different systems have very different container shapes, so the canyon itself is a very different shape in all of these, they're collapsing into a very consistent phase diagram of behavior. So that was how many flows do you get, how they're initiated. Okay, so that was the Congo Canyon story and how flows behave. One of the other things that we've seen, so I'm now going to switch for just a few minutes, and if other questions, just stop me. Kind of some of the big things that have come out, not just the Congo system, but all of the different monitoring that we've done. And the first one, the kind of headline one, perhaps except for the people who worked on that canyon, it surprised most people how active these underwater flows are. So the Congo Canyon are active for a third of the time. Individual flows can be a week long. Perhaps most spectacularly, a recent paper from my colleagues at Southampton, so Mike Clare and his group, they monitored a canyon that's 300 kilometers from the shoreline, near a shoreline, called Whittard Canyon. And that has as many flows, and they're pretty powerful, they go up to 8 meters per second. There's 6 of them in the year deployment, as Monterey Canyon has. And as you guys will know, Monterey Canyon goes all the way to the coastline, within 100 meters, within tens of meters. Yeah, this system that has 300 kilometers to the nearest coastline is just as active, if not slightly more active in that year. So we've typically put our moorings where we think there'll be lots of activity. And the joke is that Mike did a PhD with me, and we were going to go to Whittard, look at some cores. We thought it'd be really dull. It's nothing would happen, and there are better things to do in a PhD. So we never did it. And then we had an opportunity to put some moorings in it, where for biologists, that's where they're going. So that's why I put them in. Thought it'd be a bit dull. And then you got all of this data back. So it makes you wonder how many other canyons out there that are not the ones we expect to be active are actually active. But there are thousands of canyons restricted to the shelf edge globally, which are not too dissimilar to Whittard. People have looked at, this is a coastline in the Gulf of St. Lawrence, which is really rocky, with no sediment along the shelf and the coast. Yet there are 2 or 3 big flows each year here. Again, we wouldn't have predicted that. We've also been looking at Canadian fjords and finding there are more than 100 flows each summer there. So everywhere we've gone, each of the sites, it's been more active than we expected. So this is some of the previous images. So that there's been this kind of, at least for sequence stratigraphers, so this kind of emanated out of the oil and gas sector, etc. But during low stands in sea level, then these turbidity currents will be very active. But in the current high stand in sea level, except the Congo Canyon that's connected to the river, but there are only a few of those globally. Everywhere else, the model is that they'd be inactive. Except what we're finding at the moment, particularly at Whittard, is that they're active. Maybe not as active as the low stand, but still pretty active. And if you go globally, there are systems like the Bengal fan, the biggest on the planet, which is still currently active in the high stand, even though there's 150 kilometers shelf. And all of these other examples I've shown, we're beginning to understand that they're not quite as dead as people thought they were. So now we need to go out and again look at more places to understand kind of how active they are. And then that kind of leads into organic carbon cycling. So there used to be this view that terrestrial organic carbon was mainly incinerated on the shelf. So this was work around the Amazon shelf, kind of iconic work there, where you have these mobile mud layers that act as incinerators of terrestrial organic carbon as they wash it around on the shelf. And the model there is nothing reaches the canyon, and you're losing about 70% of the organic carbon there. It's really inefficient.
Incinerate means they got turned into carbon dioxide.
No, to oxidize, so remineralize, turn it into dissolved in organic carbon from organic carbon.
And what is dissolved of organic carbon?
Organic, I'm not a geochemist, as you can tell. So dissolved, you have particulate organic carbon and dissolved organic carbon. So it's defined above a certain size limit, I think, operationally. It's very fine-grained organic carbon, like a dissolved load in a river,
Okay.
rather than particles, which are larger than a certain threshold, as it's defined. It's basically for the carbon cycle. So the obvious, the big carbon clumps from the surface ocean. So the photosynthesis in the surface ocean is able to create organic matter that then sinks, and that's a drawdown of CO2 from the atmosphere over short timescales. And then only a fraction of that marine organic carbon makes it to the seafloor, where the intermediate, the rest of it is remineralized in the same way and recycled, and a small fraction of it is eventually buried on the seabed. So that's the big global carbon pump, and it operates over short timescales for atmospheric CO2 and climate. But this is a carbon pump which we think is more active than we thought with these turbidity currents. So the Bengal fan is very active at the moment, almost 100% efficient, and it's able to bury about the same mass of terrestrial organic carbon as the biological or other surface ocean pumps bury of marine carbon each year. So in terms of longer term cycles of carbon climate, these turbidity currents could be playing an important role. And if you go back to the big picture papers on global carbon cycling, so Bob Burner and others in the 80s and then others in the 90s, they're noticeable in that turbidity currents are entirely absent from any of the thinking behind that cycling. It's as if nothing reaches the deep ocean. It's all in deltas on the shelf. And they've assumed that the turbidity currents are dormant, they're dead. And they're not. So we're beginning to see that in some places, these turbidity currents are able to be very efficient at carrying the sediment and burying the carbon in the sediment. And the amount of organic carbon being buried in the fan of the Bengal is probably about what comes out of the modern rivers. So in a number of different places, fjords or other places that are very efficient at burying carbon, we're moving away from this view that we lose most of the carbon. Most of it is kind of recycled, and only a small fraction is buried. So seeing in some places, most of it's buried. So at the moment, we're trying to pick our way through that to see how, if you start to put these in kind of global carbon cycling, and you try and estimate some burial efficiencies and fluxes, how that will affect climate over long periods. If you bury the carbon in the deep ocean, then you're not able to affect atmospheric CO2 except over those long periods. Skip through. Then a third question. I'll go through these quickly. There's a slide or so on each one. And again, stop me if I'm going too quickly. The third question is really the most basic. What is a turbidity current? So this is the one I really enjoy presenting here, because there's been a debate going back to the 30s or 50s. So there's a chap, Philip Coonan, who had a paper with Coonan Miglerini in the 1950s, suggesting that turbidity currents could occur. You have these avalanches of sediment making canyons like that one, building on a paper by Daly in 1934, when people started dropping lead weights in the ocean, finding canyons, and wondering what makes those. They're not drowned river valleys, they're too deep. The other side of that argument was actually Francis Shepherd here, who was something of a skeptic about turbidity currents. And these debates went back and forth in the 50s. So there's kind of echoes of that. But the other debate is whether a turbidity current is a bit like a river. It's very dilute. There's not much sediment in. So all the sediment is being held up by fluid turbulence. And it's very dilute. And they're easy to model and easy to make in the lab. The other view is that the bit that matters in a turbidity current is very dense. It's like a debris flow. It's 30 or 40% sediment. The grains are certainly banging into each other. The settling is hindered. Excess pore pressures may start to affect the physics. The physics is just very, very different to the dilute flow. And it really matters to know what they are. Otherwise, you can't model them. You don't know whether your model's any good. So that debate about whether they're dilute or dense it's got pretty intense at times. There was one paper that had 7 separate replies. So actually we've been able to go out and we're better at measuring velocities in the flows, but we have some information about densities, and they're dense at the front, the fast ones. So the top figure here is from Congo. That's velocities. There's a hotspot of fast flow at the front of that Congo event, and that runs away from everything else in the flow that it leaves behind. And this front bit, this fast bit, is only about half an hour or maybe a few hours long, small fraction of the whole event, but it's driving everything. It's running away and shedding stuff back into the rest of the flow. And then this is from a Canadian fjord, we're able to backtrack the concentration out by an equation from an hydraulic engineer called Shazy. It's been used in rivers since the 1700s. So you take the gradient of the river, thickness of the flow, its density, and a friction coefficient. You can backtrack one of those out, they're related. We can backtrack out the density of the flow. But what we think is the frontal bit here has got densities, sediment concentrations over 10%. So for that debate, that's dense. So just the front bit is very dense. And if you want to model these things, you better worry about dense flows. And the cloud behind it is a bit of a red herring. It's just being shed backwards. It doesn't drive it.
What does flow depth mean?
That's the height above the seabed.
Oh, okay.
So this is the seabed, and these flows are about 80 meters thick. They got thicker through time. The front of it isn't very thick. The rest of it mixes and gets bigger. The ones in the Canadian fjord are a bit thinner. They're only about 10 or 20 meters thicker. I guess that I've missed a slide out, but the Monterey Canyon stuff we did with Charlie Paul was visiting a couple of days ago. There we put a large object that weighed 800 kilograms, which we thought with two other friends of it, which are the same size, would be able to triangulate acoustical. We could measure creep. They weren't meant to move, but one of them went down the canyon 7 kilometers at 4 meters per second. So it didn't just move, and it's weighing 800 kilograms, and it's the worst shape possible. It's a triangular tripod for moving it. It doesn't roll. Went for 7 kilometers, but at 4 meters per second, as fast as the flow front. And Charlie has designed, being MBOR, these kind of basketball-shaped sensors with accelerometers in, and they're about, well, a little bit bigger than a basketball. There's some of those in there, and they all move down the canyon at lockstep. This 800 kilogram monster and these little basketball shape at the same speed. So we think they were rafted in a dense layer at the base, like a debris flow, just in lockstep. So that's the other line of evidence for them being dense. We're trying to get a conductivity probe and dip it into the bottom of the flow to actually measure directly the concentration. We had one of those on a CTD, a classical oceanographic instrument on a mooring. The mooring got bent over and it beautifully dipped into the front of the flow in Monterey, measured these high concentrations for a few seconds and then broke. It had a glass kind of tube, and that wasn't going to go well. So we're trying to make more robust ones. But this classical debate that goes all the way back to Francis Shepherd, I think we're beginning to see that some of them are dense. Yeah, I've gone through this. This is how they behave. So we've kind of covered that one. Then there's the geomorphologist question. How do you sculpt the seabed? How do you make these channels and canyons? That's almost the earliest questions. So this is a fjord in Canada. This is Butte Inlet. Again, a place where the Canadians had worked on monitoring flows back in the 80s. It has this beautiful 50-kilometer kind of submarine channel down to water depths of maybe 600 meters. And these are time-lapse images by a guy called John Hughes Clark, who's kind of the godfather of this monitoring and seafloor kind of geodesy. He works in New Hampshire, the Seacom group. John's great. And he went out and mapped this channel bend. And you can see these waterfall-like steps. So like a waterfall in a river or a nick point in a river, these underwater channels also have nick points, but they migrate about half a kilometer a year. They're 20 meters high, and they basically make the channel. So in rivers, they just don't migrate at that sort of speed. And in rivers, there are external forces like faulting or uplift or sea level that makes terraces. Whereas these nick points are just made by the system internally. There's no fault crossing the channel there. And they're marching their way. There's several of them that march their way up the channel, and they are making the channel. They're affecting bends. They are dominating how that channel works. We're still waiting for one of them to get to the delta to see what happens next. We haven't seen how one originates at the bottom yet, but we're going back every year. We live in hope. But again, very different to a river that has a point bar and secondary flow that sweeps the sediment to the inside and make a point bar. These nick points are just dominating. So those nick points are just offshore here. So this is an AUV survey from Charlie's paper, with these beautiful networks. It looks incredibly active. So it'd be a really interesting thing to go back and time lapse this canyon, and has this baseline survey already, and try and see how it's working. This is some of the best baseline data anyway. And then for the geologists, it's usually most of my audience with turbidity currents are geologists who work on rock outcrops. I'm still trying to get as many of them as possible to become oceanographers, I guess. I used to be an outcrop geologist. I think it's better to measure the things as they happen rather than look at a layer of sand and mud. And quite often when I was going to conferences, we go on field trips, you'd have 5 different geologists looking at the same outcrop of the turbidite, and they'd have 5 very different models for how that formed. And the only thing I was sure about is that I wasn't sure of that. I think all 5 of them could have been right, all 5 of them could have been wrong. So it's difficult to know for some things. But we're beginning to try and link the direct monitoring to actual coring of the seafloor. So as people here will probably know, that has its own challenges. Sometimes we're not able to core it on a second cruise until a few weeks or months later. But one of the things we did, this is the delta front of this thing in Canada. And there's a river that has a delta lip here that builds out and then collapses. These are channels that go down front of the delta. And there are these remarkable bed forms called cyclic steps, jargon for it. And they march their way back up slope. So they're supercritical flow features. There's been a lot of debate about what would they produce in the rock record. And we were able to core the same areas as this time-lapse image, put some moorings out with ABCPs to measure the velocity and link that to coring of the deposit. And also, if you time-lapse the seafloor, you can make synthetic stratigraphy where it builds up and where it erodes. So these are kind of timelines, but they're kind of an imaginary stratigraphy. So we're trying to connect it into the geological side of things. And of course, you can only do things that happen over a short period, whereas rock outcrops go for thousands or millions of years. So we're on a short time scale. And then I think this is the last slide, yeah. The last thing that's got really interesting is whether turbidity currents can record other hazards. So as I'm chatting to Wenyan, there's been a vigorous debate, particularly for the Cascadian margin, about whether these flow deposits, turbidity current deposits and turbidites, can record the major earthquakes along the Cascadian margin. And there's been a hypothesis, it's an interesting one, that every time there's a very large earthquake there, it shakes the seafloor, you have landslides that disintegrate to these flows, and you make one of these turbidites, you can map and correlate across the whole. So then it's easy, you just correlate and date them, and you've got your earthquake record. The problem is that when you try and correlate them, you're doing it with radiocarbon dates that have uncertainties of maybe 100 years, certainly 50, sometimes 200. The events are only 200 years apart. They might actually correlate, but you can't tell. But this debate's been going. So this is one of the other areas, and also whether you can record floods or typhoons in the deep sea. So we're making some progress. Usually when there's a major earthquake, such as the Kaikoura one in New Zealand, people went to the seabed and they knew what the earthquake was and when it happened. So for once you're sure about something, and then you can see what sort of deposit is where on the seabed. And it's a great way of testing it. You just have to wait for the big earthquakes. So that's kind of a run through of the Congo project at the beginning, and then some of these other really fundamental questions. What is a flow? How do they work? And things that we just assumed for rivers. We knew the answer, we don't ask what the river is. It's dilute. So in the future, what we're hoping to do is, the problem, as you saw at the beginning, is that if you put a mooring which has a float and an ABCP looking down, it has the wire and then an acoustic release, and then its anchor is down the seabed in the flow. So your sensor is above the flow, but your anchor gets broken. So what you want is a technique where you can put sensors outside the flow that don't break, and you don't have to go chasing moorings around the Atlantic. So we're quite excited that a series of ocean bottom seismometers along the Congo Canyon have picked up a nice signal, strong signal from these underwater flows, and those are outside the channel. So I think the future may involve seismologists, which I'm not. So this is a high frequency signal for the turbidity currents of 2 to 10 hertz, although they weren't broadband instruments, so it could actually go to lower frequencies, we don't know yet. But this could really change things. And I guess we're also trying to do this in more places to understand global fluxes. Everywhere seems to be more active than we thought. We now want to put sensors where we think flows might not happen. We weren't brave enough to do that last time, but they're the biggest surprises. So kind of to roll this out to more places, we need to measure the sediment concentration. That's what we're bad at. But it's kind of exciting time. It's like getting the first measurements directly in detail from rivers, a few streams and then a medium-sized river and then one big river, and finally being able to test the models. So just to conclude, that's the seismic data from the Congo. So these are the signals in flows. I can show people this afterwards if they're wrong. Each one of those is an ODS record through time, in shallow water to deep water. This is the Congo 2020 January event, and it broke our moorings when it arrived. From the seismometers, we get a full time series. We're able to see how many pulses it's made of, how long the pulses were. So we're beginning to understand what it did. And our moorings just got trashed when it arrived, so that's the advantage. We can calibrate that against the flow velocities from the other moorings, so we know what speed of flow makes the seismic signal. So yeah, La Jolla will be an interesting place to go. It's very classical. There are these amazing baseline surveys. It's a good size to work at. It's got resources very near to the top of the canyon, so this would be an interesting place to go back to. There are these classical models for a submarine fan that have these canyon channels bifurcate like a bird's foot delta. That's the old map. I think that's a Dave Piper paper from maybe the 90s, 80s, maybe far back in the 70s. And this is an AUV survey of the same area. And there's only really a single channel and the weird features. So it's just not like a submarine fan model. And maybe that's moving out there. Fun to do that. And then just to mention some stuff with Wenyang, we're excited about measuring turbidity currents in action, and bar some of the data from here, etc. Some people thought that was impossible a few years ago in this level of detail. That was probably the consensus. But then you get to underwater landslides, so they are able to make turbidity currents for a distinctly different thing. And as far as I'm aware, an entirely underwater submarine landslide has never been measured in action directly until recently. So I don't know of any examples. There are Norwegian fjords where the landslide eats its way back onto land. You observe a bit on land, but otherwise all we had was post-event surveying. We'd never actually, and terrestrial landslides on land, we have thousands of direct observations and video clips and pore pressure measurements and thousands of them. I don't think there's a single one from underwater landslide anywhere on the planet until this one. So I'm very excited about the possibility of using seismic signals to tell you, well, actually not only that a landslide has happened underwater, but if you have the right array geometry where it happened, and then you start to be able to understand what triggers it. So there are lots of models for what triggers an underwater landslide. None of them are tested particularly. So this was probably the most interesting paper I've seen. I had the conversation with Charlie Paul about what was our most interesting paper we've ever seen. And this is my vote. So hence the visit here. But it changed the game. You can monitor these things on the scale of the Gulf of Mexico. So this is, if people have seen it, it's a paper looking at landslide seismic signals on the scale of the Gulf of Mexico using a terrestrial seismic array. So it's a game changer. And the really interesting thing is in that period of 7 years, you're better than me, there are 85 of these underwater landslide signals, and 75 of them are just after an earthquake, but the earthquake can be thousands of kilometers away. So they're remotely triggered, not by local earthquakes, by something the other side of the continent. 75 times out of 85. It's not a fluke because those earthquakes only occupy less than % of the whole time. You can't fluke it. So that would really change the view of how underwater landslides are triggered. There's some local site effects whereby that ground motion is accentuated, and somewhere 1,000 kilometers that way is triggered. It's a total game changer. So I think the submarine landslide monitoring, which I always thought was impossible, might be possible. So that changes the game. So this is some of the stuff from this paper. So this is really part of the visit here, is to see whether this can be, I guess the first thing is to go to the seabed, triangulate accurately where the signal comes from. So you can actually go and repeat multi-beam it and show there's a landslide scar there and a recent one before your previous survey. If you do that, then you validated it against the field data, and then you can roll it out in different places around the world, and it gets exciting. So we're talking about various projects in various places. So I'll leave that there. I think is that just about time.
Thank you, Pete. Excellent talk. We would first like to invite questions from the students.
Okay. Thank you for the great talk. It's a super interesting topic. And so I have a lot of questions, but I'll just ask the main one in my mind right now. You showed this animation of a channel bend and how it changes, its sediment features change over time. You said that the channels, I quoted here, the channels are being made by the system itself.
The nick points are these step-like features that are migrating up the channel. And in a river, you need sea level to go down and make a terrace. We have a fault that makes a step in the river profile. So there are external things making those steps.
Right.
And those external drivers are absent in that system. So that the nick points are being made by some internal behavior in the system.
Yeah, so my question was, what does the system encompass in your view? Because I'm a physical oceanographer who has studied turbidity currents, and most of the time when I look at research on this, people seem to forget that there's water on top of the turbidity
There's
currents.
not much crossover between disciplines.
So how big do you think is the potential for the background ocean dynamics to be causing those changes?
So there is actually eventually some work on how thermohaline contour currents moving at tens of centimeters per second can affect these flows. Will obviously divert them, but the front bit of the flow, the dense bit, the debris flow like bit, is maybe going at several meters per second, maybe 8 meters per second. I don't think they affect that bit, but the dilute trailing cloud that's billowing behind it is not traveling much quicker than a few tens of centimeters per second. They'll definitely carry that around. If you have internal tides in the canyon, which you obviously do, then you have tailwinds or headwinds of that magnitude that will again affect the flow. So just comparing the magnitude of velocities, they will have a big effect, but only on some parts of the flow. They're really dense and fast. Bit at the front, probably not, but everything else. The mixing is a kind of physical oceanographer's game. The numerical models for these flows, they can never get them to work. On the computer models, because they mixed so efficiently with seawater, it became enormous before they went a few kilometers down the numerical model. So we've tried to understand how that mixing dynamic works. The sediment settles out, so it's not like a salt.
Right.
So there are things like that, and the interaction with contour currents, and breaking internal waves on the shell at critical angles that could be triggering these sediment. Resuspending sediment when it makes one of these flows. So there are all sorts of possibilities.
Thanks.
You're totally right. They don't talk to each other.
I was curious if you showed the sort of black and white picture or video, and you said that there were features that were sort of moving back up, closer to the delta, I guess. And I was curious, and maybe this is a question that would take a semester to answer, but why are they moving in that direction, and how does that work?
It's a good question. So in a river, you have this bed form diagram where as the flow gets faster, you go from ripples to dunes, but they all move down the river channel. And then if you keep going faster, you end up in what's called an anti-dune or supercritical flow. And every flow of the fluid has two states. They can be thick and slow, and then they become thin and dense with a hydraulic jump. So if you pour water into a sink, it starts off as a thin layer and fast, and as it spreads, it becomes slower. You get this circular hydraulic jump. So there are two states, and the thin and fast state is supercritical. And bed forms made by those sorts of flows tend to migrate up the slope. So there is a class of bed forms that go up slope, even in rivers. But underwater, the density differences, there are factors that make them much more common than seabed. The bed form diagrams are just different.
Thank you.
They're common as well. They're in this canyon. So those sorts of bed forms.
Any question from the general audience?
Sort of impressed by the volume material from the Conga example. I was wondering how
Yeah.
How large the flows have to be before you could see it with gravity data, like
Yeah, I did wonder what
grace or with
you made of this.
sea surface.
Some of the,
Right.
yeah, it's a good question. I guess you may know more than I would. The dimensions of the change on the seabed is maybe an average lowering of the seabed on the axis of the canyon by 20 meters or so. But it's not uniform. It's very patchy. There are these step-like waterfalls. It's maybe 30 or 40 meters there, and then there's nothing. Another one, the waterfalls. So the magnitude is a couple of tens of meters, 200 meters across on the axis, and then all of that material has been spread somewhere, probably as a meter or two thick layer of a huge. It's got a total volume of several cubic kilometers. So yeah, it's an interesting question. The underwater landslides, this isn't very big. So the Strega slide you may have heard of off Norway has a volume of 3,000 cubic kilometers, not 2 or 3. And that and its isostatic response and how that would have been, how that affects things. They get much bigger as well. Yeah, it'd be interesting. The volumes are big.
Stupid question. What's the difference between submarine landslides and turbidity currents? Is it their scales or?
I get asked that in grants as well, including one recently. So a landslide is a coherent block of material, like a landslide on land. The turbidity current has mixed that landslide material with seawater, so it's much more fluid. So it's more like you'd imagine a kind of flood in a river. So it's at least partly turbulent. It's reasonably dilute, and all that water is mixed with the landslide. A landslide is a more rigid block, more coherent block.
In terms of volume or the amount of solid material being transported, are they comparable?
It depends on, so the initial, for a turbidity current, you can trigger them from a landslide. So the landslide is not the only way, but it's commonest maybe. So the landslide has a volume to begin with. That volume, if it all mixes with seawater, makes the same volume of sediment and turbidity current. But then what we found in the Congo is the turbidity current erodes the seabed and brings in more sediment, and it could become at least 30 or 40 or 50 times bigger. So it can get much bigger than the initial landslide. So they can be different scales. If the landslide is huge, but it doesn't mix with seawater, it's very slow, it will make a very small turbidity current. It could go either way.
So you can transform between the two things.
Yeah, as you bring in seawater, you evolve from one to the other.
There's a question from Matthew Alford on Zoom. So Matthew, would you like to mute yourself? Unmute yourself.
Oh yeah, hi Peter. My name's Matthew. I don't think we've met. I'm a physical oceanographer here, and Noel was the first student who asked a question. He was being a little bit too humble, but I guess I would challenge your assertion that we've never caught a submarine landslide in the act. And I put a citation to his paper in Science Advances in 2019 in the chat.
Okay.
And then
Where was it?
That was actually in a lake in Mexico. So certainly nothing near the scale of the Congo or anything like that. But I thought it was a really beautiful paper that he and his former advisor did. So direct you to that one and encourage you to talk to Noel a little bit more. And then the other point I just wanted to make is that, yeah, we've kind of taken over the La Jolla Canyon in recent years as our own little sort of internal tides and turbulence playground. And we have a 1 year long time series that Drew Lucas was involved with us as well. And it would be really fun to have you take a look at those data if you're interested, and we could talk further.
It'd be super cool. I think you have the skill sets that are more useful than some of the more geological skill sets for the flows. So I was also wondering how much more had been done here. I was rather feeling nervous about presenting this particular place because of what people must have done here. Yeah.
Well, we had the same surprise that you did. I think before we started move back in as physical oceanographers, it had been a long time. I think you mentioned Shepherd. It had been decades and decades since real physical oceanography had been done in there. I know the geologists and biologists have been in there. But anyway, we'd love to talk to you more about it. And yeah, we were certainly terrified about all of our moorings getting mowed down by one of these turbidity currents too.
Yeah, we've tried moorings that have 2 anchors. So there are 2 lines, and you put the anchors outside the main axis. We've got that to work for small channels. And we think we've now got a way of doing it for bigger, you have more line on deck. But there may be ways of making moorings that have better chances of surviving, which definitely increases your morale.
Sure. Anyway, nice talking. Thank you very much. Looking forward to talking to you more.
More, yeah.
Hey, if there's no more question, let's thank Peter again.
Thanks for this time. That's the time of life as well.